Hi everyone and welcome back. Today we're going to be talking about nuclear magnetic resonance spectroscopy, or NMR, in particular proton NMR or 1H NMR spectroscopy. In this video we're going to look at the theory, so the type of electromagnetic radiation that gives rise to these signals and why, and a quick look at low resolution spectra. In the next one we will look at high resolution spectra and what kind of information we can actually get from this as we interpret the spectra. So as with all types of spectroscopy, we are looking at the interaction of molecules with radiation from a particular region of the electromagnetic spectrum. You may recall that we had AAS is within the visible spectrum, UV-Vis covers both of these. We talked about infrared, which gives us information on functional groups due to the vibration changes in bonds within molecules. And now we're going to look at radio waves. So these are the same radio waves as is picked up by a radio station, or an analog radio station at least anyway. And we can tune these frequencies in to respond to particular atoms in a molecule. And in this case, majoritively of the time we're looking at doing proton or hydrogen. So we're probing the hydrogens within a molecule. So NMR uses energy in the radio frequency of the electromagnetic spectrum, which causes change in the spin of the particles in the nucleus. So AAS, we were looking at energy transitions within the electron cloud, so from high energy to low energy, ground state to excited state electrons. Infrared, we are looking from low energy to high energy vibrations within the bonds of molecules. Now we're actually probing energy transitions from low to high within the nucleus of the atom. This can be done because of a property known as spin, or quantum spin. Subatomic particles possess this property known as nuclear spin, and certain nuclei with an odd atomic mass, so an odd number of nucleons, will have this property. They have what we call a magnetic spin moment. These are hydrogen 1, carbon 13, even phosphorus 31. Okay, the most common ones and the ones that we look at within this course are hydrogen and carbon, because of course they're present in all organic molecules that we want to be able to identify. Because they have a spin, so if you imagine a nucleus with a spin, every time we have a spinning charged particle, it creates a corresponding magnetic moment. So these atoms, these nuclei, when they spin, act like tiny little bar magnets, which is what this is showing here with a north and a south pole. If we place these inside an external magnetic field, so get a really large magnet and sit them within this field, there are two possibilities for the way they can align. They can align with the field, or they can align against the field. If they line against the field, it's like a fish ship swimming upstream, okay? It's going to take more energy. So when they align against the field, this is the high energy orientation, and when they are aligned with the field, so when they're going with the flow, this is the low energy. There is a difference in energy, and we can make them transition from one to the other. This is what we call a spin flip. When we make the nuclei spin from one state with the field to against the field, they absorb energy to do so. So nuclei that are aligned against the field are at a higher energy. If we supply radiation of the correct wavelength that corresponds to the frequency required for, say, a proton nuclei, then that energy is absorbed, and the nuclei undergoes what we call a spin flip. So it then goes into the higher energy state. We can measure that absorption of energy and its decay to get a signal from that particular proton. When we do this, we graph this frequency, so where that energy was absorbed from, and plot it, and we can start to get a picture of the molecule. So NMRs can be quite large, or even with modern technology quite small, and when we go to Melbourne Uni you will see some of the NMR machines that they have in the facility there. The two most common forms of NMR, as I said, are hydrogen, so 1H NMR, and we refer to this as proton NMR, and carbon-13 NMR. Okay, so as we said, it needs to have an uneven number of nucleons. So carbon-13, the isotope of carbon-12, is able to be detected using these techniques as well. So this is what a typical NMR spectrum looks like. There are a two-dimensional graph. The chemical shift is given along the x-axis here in what we call delta ppm, or parts per million. And it's plotted against the intensity of the absorption signal. So this is our signal here that we refer to as a peak. The graph starts at 0 and works backwards to the left in relation to TMS. And TMS here is essentially what we are calibrating the machine against. So they put a small sample of TMS, which we will learn later on, which is tetramethylsilane. They set that to being 0, and then everything else is measured relative to TMS. The delta ppm values give us some information. The chemical shift gives us some information as to the nature of the groups that we're looking at. And then we can also get information from the number of peaks, the splitting of the peaks, and their chemical shift. And most of this information is given in our data book, so we just need to be able to refer to it to be able to solve spectra. If we have a look at this one here, we can see that when we talk about environments, these protons are going to be the same as these protons, which is why they're colored the same. The protons here are attached to a carbon, which is attached to a chlorine next to a CH2. So this molecule has symmetry. So this is one environment for protons, and this is another environment for protons. We can only see the protons in a molecule, so we do not see the chlorines in the spectrum. So we can see that there are two environments, two sets of peaks on our spectrum. One is what we refer to as a triplet, one a quartet, and we will talk about splitting in our next video. So as I said, TMS is what we calibrate the machines against. This is tetramethylsilane. Okay, so it is a silicon with 4 methyl groups. If you are asked to draw the structural formula of tetramethylsilane, it is important that you include all bonds, remembering that VCAR wants us to show all bonds when drawing our structural formulas. TMS is used as a standard for a number of reasons, that being that all the hydrogens in this molecule are within the same environment, so they form a single peak, giving a strong signal. Also, because it uses silicon in the central, it has an effect on the machine that pulls this chemical shift outside of that would interfere with most hydrocarbon-based molecules. Okay, so this means that we can use this without it interfering or putting a peak within the region that we want to look at for analysis. So chemical shift is a property that we see dependent on the bonding environment of the protons that we're getting the signal from. Okay, so because each of these spinning nuclei have an inherent magnetic field, this will affect the magnetic fields of other atoms around them. So we get what we call nuclear shielding, and this depends on the different atoms that it's connected to. What this means is it changes the frequency at which the peaks are found dependent on their bonding environment, which is incredibly useful. So a chemical shift of, say, 1.3 means that the hydrogen that caused the peak is 1.3 millionths less than the field needed for TMS. So this is what we mean by delta ppm. We don't need to know about that too much, other than the environment that the protons are in will shift it downfield away from TMS, dependent on what it is attached to. And the more electronegative the atom that the hydrogen is attached to, the greater the shift. So we will tend to find hydrogens attached to oxygens around 5, and then carbonyls or acids, the hydrogen of an acid will be even higher. Okay, so the shift can tell us about the environment. So because this is not a specific thing, we're looking at ranges of chemical shifts. And if we see a chemical shift that is higher than what we are expecting, this is usually due to the presence of a highly negative element being near the proton that we're looking at. So electron density of these electronegative things can shield the nucleus from the electrical field, or it can de-shield it, allowing the radiation to get into the nucleus easier, causing the frequency of which that spin flip occurs at to be different. So what we really need to know is that the nature of what is attached to the group we're looking at can influence its shift. So we can look at the data booklet, but be prepared that they may change around a little bit. So let's look at a couple of quick low resolution proton NMR. Essentially in an NMR, the number of peaks tells you the number of different environments of hydrogens that there are. If they are connected differently, they are a different environment. Okay, and then what we call the integral ratio gives us the area under the peak, and that gives us the relative number of hydrogens in each environment. And then the chemical shift can give us information about the type. So let's have a look at a low res of ethane. Ethane has 6 hydrogen atoms. They all are in the same environment. These 3 hydrogens are exactly the same as these 3 hydrogens. I have symmetry in the molecule. There is nothing different in any of the bonding. Therefore, it is a single peak that is seen in the NMR. However, if we change this, you'll notice if we go to chloromethane, we now have 3 hydrogens, and where we saw the CH3 in the previous one resonating at 0.9 chemical shift, which is characteristic of a pure alkyl CH3, we now see that this has downfield shifted due to de-shielding of the chlorine, and it appears at 3, much higher than the previous one. So if we have a slightly more complicated molecule of chloroethanoic acid, we can see here that these hydrogens are going to be different to this hydrogen. This hydrogen here is attached to an oxygen of a carboxylic acid, while these are 2 hydrogens on a CH2. This means I have 2 environments. I will see 2 peaks. The one that will be closer to 0 will be the CH2, and then this hydrogen of the carboxylic acid will be downfield shifted to 11.2, and we can see those in our data booklet as well. The integral ratio of this, the peak that corresponds to this one will have an integral ratio of 1 is to 2, so the area under those curves will have a relative ratio of 1 is to 2. If we look at ethanol and we draw out the structure of ethanol, okay, now we can see where we start to see different environments. We have this environment here of the CH3. The 2 hydrogens here are attached to the carbon that has the hydroxyl attached, and then we have this one here. So we have 3 environments, so therefore we see 3 peaks. And we see that here. We have 1, 2, 3 peaks. The one closest to 1, if we look up the chemical shift, is going to be our CH3. And then if we look up the chemical shift for this one in our data booklet, we will see that CH2s attached to an oxygen will appear between around 4, 4.5, and then the OH here is our 3rd environment. We can also check the integral ratio, and if we were to measure these, we would find that this is a 1 is to 2 is to 3 ratio. The splitting that we see here in these groups of peaks is also indicative of the environment that we're in, and we'll look at that in our next video. Again, ethanoic acid, it has 2 environments. We see 2 peaks. And that is it for looking at low resolution spectroscopy. I know it all seems a little bit confusing at the moment, but we will have a bit of practice and it will start to coalesce once we start looking at a few questions. So good luck, and I'll see you in class.